slide 16. Okay, 16. The term bioenergetics, that is also finished, I think. Next, free energy. This free energy, we from this free energy we can start. We have some light discussions on free energy. Free energy is the energy available for performing works. What work? Cellular work. Cellular work. What cellular work? Cellular work means protein synthesis. Protein synthesis is the most important function. Then the operation of the membrane transport systems, operation of the organelles. Okay, these are the cellular functions. Okay, okay. Suppose synthesis of glycogen, synthesis of urea, all these require energy. Without energy, it is not possible. Urea synthesis, glycogen synthesis, even synthesis, that synthesis of ketone, that also require, and synthesis of cholesterol, all require energy. Synthesis of fatty acids, okay, these are the cellular works. For performing cellular works, this free energy is available, is required. Energy that is bound, energy in broad sense, we can think energy as two forms. That is, one is free form. This free form is required for performing cellular works. In another form, that is bound form. That means when energy is excess, when, as for example, immediately after meal, when energy is excess, that energy is stored in bound form, in the form of ATP. ATP is, that means synthesis of ATP, in that means energy is bound. Energy is bound, and that energy which is not required, that is stored as ATP in the cell, and when necessary, the hydrolysis of this ATP provide the free energy. I mean that free energy is release of free energy is accompanied with works. Okay, am I clear? Am I clear? Okay. Then free energy, negative, positive, you don't understand this, as you are not first year student, but second year students. Exergonic reactions, endergonic reactions that are accompanied with release of energy is called an exergonic energy. Exergonic reactions, chemical reactions that consume energy is termed as endergonic reactions. Catabolic reactions are exergonic reactions, and anabolic reactions are endergonic reactions. These are the very basic ideas. Okay. Okay. Next, we try to be more attentive. Next question, important question: high energy compound, low energy compound. That energy that is stored, that storage energy is in two forms. One form is high energy phosphate, another form is low energy phosphate. Examples of the high energy phosphate: ATP, GTP, creatine phosphate, phosphanol pyruvate, even carbamyl phosphate. It is not shown. Carbamyl phosphate has not been shown here. And this 4, it is, I think it is sufficient. ATP, GTP, even CTP, and creatine phosphate is here, and phosphanol pyruvate. These are the high energy phosphates. compounds that entrap use free energy, that compounds that store use free energy termed as high energy phosphate compounds. Okay. Hydrolysis of these compounds release free energy more than that of ATP. So this can be again the high energy phosphate can be defined again in the way in another fashion, that is compounds that release free energy more than that of ATP can be termed as high energy phosphate compounds. Examples include ATP, GTP, creatine phosphate, phosphoenol pyruvate. Okay, is it clear? So any compound that release ATP more than that of ATP is called high energy phosphate, high energy phosphates. Low energy phosphate. Low energy phosphates entrap less free energy. Less hydrolysis of these compounds release free energy less than that of ATP. Less than that of ATP. So these examples of low energy phosphate: glycerol 3 phosphate, glucose 6 phosphate, fructose 6 phosphate. These are low energy phosphates. You see, ATP hydrolysis of ATP gives 7.2 or 7.3 kilocalorie per mole of ATP, whereas hydrolysis, that is hydrolysis of glycerol 3 phosphate release only 2.2 kilocalorie per mole of glycerol 3 phosphate here, and this glycerol 3 phosphate, glucose 6 phosphate, they will be releasing energy, but their release is less than 7.35, and it is negative. And why it is negative? It is negative because these are the exergonic reactions releasing energy. That's why it is negative. Very simple to understand. Is it clear? Even synthesis of ATP, that also require ATP. Without consumption of ATP synthesis is not possible. Okay, mind it. For energy, ATP synthesis, energy is required, and ATP itself is containing energy. Okay, to the point. These are repetitions. That's why we cannot spend more time. Biological oxidation. Okay, biological oxidation. This is in simplified way to define biological oxidation. Oxidation within the biological system is called biological oxidation. Is it a biological system you understand? Within cell membrane. Within membrane, organelle membranes. Okay. Biological oxidation. In biological oxidation is always accompanied by reduction. Is it clear? It should be made clear. Okay. Suppose here there is two compounds A and B. Okay. From A, if electron is lost, this is called oxidation, and that electron, when is taken up by B, that is reduction. Okay, that is called reduction. So loss of electron can be termed as oxidation. Acceptance of electron can be termed as reduction. This the which enzymes this is the main point. Biological oxidation is not alone. It is always accompanied with reduction also. So that's why we say oxidation reduction oxidation reduction couple. Okay, and this requires some enzymes. They are called oxidoreductases. Oxidoreductases, dehydrogenases, oxidases, peroxidases, catalysases, oxygenases. These oxidoreductases uh, are the function for function of oxidation as well as reduction. And as we mentioned previously, oxidation is always accompanied by reduction. That's why they are termed as oxidoreductases. In enzyme classification, can we remember oxidoreductases? Oxidoreductases. Okay. Mechanism of biological oxidation, very simple to mention. Very simple. Addition of oxygen. This is definition from our SSC and HSC level classes, intermediate level classes. Removal of reducing equivalent. This is from HSC level, and at this level of graduation, we must remember that removal of electron is termed as oxidation, removal of electron. Okay, is it clear? So reduction, that means acceptance of electron is termed as reduction. The purpose of biological reduction oxidation is production of energy. Production of main purpose is production of energy. Okay. Next come to the principles. This principle of biological oxidation is very important. You know this. Complex organic molecules are degraded into two carbon compounds. That means whatever we take, carbohydrate, protein, fat, that is ultimately converted to two carbon compound acetyl CoA. Acetyl CoA. Next point, this acetyl CoA in citric acid cycle is completely oxidized, forming carbon dioxide and reducing equivalents. These reducing equivalents are taken out by coenzymes, and these coenzymes transport this reducing equivalents to respiratory chain. In respiratory chain, the reduced coenzymes are oxidized, reducing equivalents, and from these reducing equivalents, ultimately, energy is produced. The reducing equivalents are transported through the respiratory chain, electron transport chain, that ultimately combine to form water and energy. Water and energy. Here, percentage students, it is still I find low. What these students are doing, I don't know. In these days, must have uh, must they could have accompanied with us to share their knowledge, to share their knowledges and ignorances. Is it clear? Ignorances must be replaced by knowledge, sound basic knowledge. Addition of we sometimes ask in the exam most basic ideas. Define phosphorylation. Define phosphorylation. Is it clear? This is not oxidative phosphorylation. Simple oxidation, phosphorylation. Addition of phosphate group to AMP and ADP to form ATP can be termed as phosphorylation. And these phosphorylation are of two types, basically. Oxidative phosphorylation that occurs respiratory chain releasing most of the releasing bulk of the energy. Okay, and oxidation can also occur in substrate level. Is it clear? That is also called substrate level phosphorylation. Substrate level phosphorylation. Is it clear? Is it clear that one sixth bisphosphoglycerate when converted to glyceraldehyde phosphate, then some energy is produced. That is at substrate level. Is it clear? Again, it can be produced when when phosphanol pyruvate is converted to pyruvate, and some energy could be produced. Again, within the TCA cycle, some energy is produced. Substrate level energy is produced when succinyl CoA is converted to succinate. Succinyl CoA must be fluent with the components of the citric acid cycle. Citric acid cycle that again include citrate, isocitrate, alpha ketoglutarate, alpha ketoglutarate to succinate, succinyl CoA to succinate, succinate to fumarate, fumarate to malate, malate to oxaloacetate, and that oxaloacetate again condense with acetyl CoA to form citrate. Citrate. Is it clear? I think this should remain in your mind. Now come to the point. This is most frequently asked question: oxidative phosphorylation. Oxidative phosphorylation. ATP synthesis coupled with oxidative process can be termed as oxidative phosphorylation. Oxidative phosphorylation. Okay. In another way, the oxidative phosphorylation is the process by which free energy is entrapped in high energy phosphate in ATP. It is the process by which free energy is entrapped in ATP. This is definition according to Harper. According to Lippincott, we can define it is the coupling of electron transport with ATP synthesis. Is it clear? Coupling of electron transport with ATP synthesis can be termed as oxidative phosphorylation. Oxidative process coupled with phosphorylation can be termed, phosphorylation of ADP can be termed as oxidative phosphorylation. Be clear. Be clear. Okay. Definition of oxidative phosphorylation. Next. Now come to the point we mentioned, respiratory chain. Respiratory chain, this is the unique enzymes, hundreds of enzymes located on the inner mitochondrial membrane. Inner mitochondrial membrane. Okay. Let us have a view. This is the respiratory electron transport chain. It is very near to the inner mitochondrial membrane, and throughout this portion, the inner mitochondrial membrane is studded with the enzymes of the respiratory chain. Is it clear? It is a gift. It is God's gift, Allah's gift to human being, to nature, to whole of nature. Okay. So definition, as we know, we will be not wasting time in respiration. And it is the highly organized chain of enzyme complexes arranged in order of increasing redox potential in the inner mitochondrial membrane. Its function is to transport reducing equivalent electron proton. It's another function, production of energy, obviously free energy, and this from this free energy, ultimately ATP is synthesized in complex 5, complex up to complex 1 to 4, that are the constituents of the respiratory chain. Complex 5 is outside the respiratory chain, but in close association, but in very, very close association with the respiratory chain responsible for ATP synthesis. Okay, then the electron transport is another definition. Lippincott have been put, that is, electron transport chain is the final common pathway of by which electrons derived from different fuels of the body flow to the oxygen. Very good definition. Electrons uh, they should not be allowed to move in the body like stray dogs. Is it clear? If they move like stray dogs, then that can produce disaster. They can damage all the organs. In that case, life of the human would have been reduced to few minutes. Okay, so wherever there is electron, free energy, that is ultimately transported to the respiratory chain, and that respiratory chain disposes those free energy electron, okay, that is these electrons to form the energy ultimately. These are redox potential we mentioned. Redox potential, that means the components of the redox potential include oxidized NAD. Suppose I am given an oxidized coenzyme and reduced coenzyme. Here oxidized coenzyme is, say, NAD, nicotinamide adenine dinucleotide, and a reduced coenzyme is NAD2H. NAD2H, is it clear? And they are in pairs. FAD, H2, FMN, FMNH. FMN means flavin mononucleotide. Is it clear? This FMN is the oxidized form of coenzyme. FMNH2, that is the reduced form of coenzyme. Now come to the point, one point about increasing redox potential that I mentioned that I should have to explain. First, you have a view of location of the respiratory chain for a few seconds. Okay, complete. This electron transport chain. This is the electron transport chain. Its components include complex 1, complex 2, then complex 3, complex 4. These are the components of the respiratory chain. Okay. The electrons are transported from complex 1 to complex 2, complex and coenzyme Q. Why? Because of increasing redox potential. That means the tendency for losing electron here, this whatever it may be, but the tendency of accepting electron from this complex 1, from complex 1 this this this, okay, complex electrons move from complex 1 to coenzyme Q. Time is being over, but a percentage is being given. Okay, electron will move from complex 1 to coenzyme Q because of increasing redox potential. The capacity to hold electron by complex 1 is less than that of this coenzyme Q. That's why it will the coenzyme Q complex one will transfer that electron to coenzyme Q. Is it clear? That means coenzyme Q, it is it is the coenzyme that is almost snatching the electron from complex one. The same similar thing happens from complex 2 to coenzyme Q. Is it clear? And from coenzyme Q, these are the points. Yeah, these points, complex 1, complex 2, these are the points where reducing equivalent is splitted to electron and proton. Okay, electrons move horizontally, protons move vertically. Protons move vertically. Is it clear? You may be questioning that what about this complex 2? Complex 2 cannot split electron protons. It simply transfers reducing equivalent to coenzyme Q, and coenzyme Q splits that reducing equivalent. Okay, if it cannot, it transfer it to complex 3. Okay, so this complex 3, it is also splitting electron proton. Electrons move horizontally to complex 4 and proton vertically. Protons vertically. Even complex 4, which is the uh, final that is stopover of respiratory chain, uh, it also splits electron, the reducing equivalents to electron proton. Is it clear? Electron proton. Protons are transported vertically, and electrons here, that means it is horizontally. Ultimately, this is the point where electron and proton unite together to form reducing equivalent. Is it clear? So the journey of this electron from this complex 1 to complex 4 is like moving from a downhill. That means from the top of a hill to the down of a hill. Is it clear? If from the top of a hill, if I just put a piece of brick, it will automatically fall to downwards. No force will be required. No force. Just under the action of gravity, by the action of gravity, it will fall to the bottom. The same thing happens for the electrons. Is it clear? So this is very interesting to understand. This is very oversimplified diagram to show components of the respiratory chain in a more complex way, in a more precise way. We should view like this. Complex 1 include NADH dehydrogenase, FMN. NADH dehydrogenase is the enzyme, FMN is the coenzyme. Is it clear? These two constitute complex 1. NADH electron from this NADH comes to the FMN. FMN cannot keep it because this affinity of coenzyme Q is more. That's why electron moves to ultimately coenzyme Q. Okay, and we mentioned the succinate dehydrogenase. Its coenzyme is FAD, flavin adenine dinucleotide. Is it from FAD? It moves to, that's reducing equivalent is moves to coenzyme Q. It do not split reducing equivalent. The reducing equivalent is split in the coenzyme Q. If it cannot, it transfer it to cytochrome reductase. Cytochrome reductase. Is it clear? So protons, the intensity, the tendency of moving electron to cytochrome reductase is increased many times. Okay, and it is increased in many times, and ultimately electrons move to cytochrome C. Cytochrome C, this is not component of the respiratory chain, but ultimately from C to because this is simply because it is not on the inner mitochondrial membrane. Okay, it is on the a bit outer aspect. In the inner mitochondrial membrane contains this. Okay. From cytochrome C, it is ultimately transported to cytochrome oxidase. Cytochrome reductase is complex 3. Cytochrome oxidase is complex 4. Electrons are transported to cytochrome oxidase. Here, electrons unite with proton. There is very intense desire for the meeting of electron and proton here, ultimately forming reducing equivalent, and that reducing equivalent, that means 2H. It is also it has also intense desire to meet with to meet with nascent oxygen to form water. Is it clear? In this is production of water, only water. How energy is produced? Yes, energy will be produced. This person is late introduced entry. Electron will be produced. Energy will be produced by this proton transport. Okay, this is a view. This is from a book that is the edition with English, that is a biochemistry book to show the simplified view of the respiratory chain. This is the inner respiratory membrane, and this inner membrane, this portion is outer aspect of the inner membrane, and this portion is inner membrane of the respiratory chain. Okay, this is complex 1, this is coenzyme 2. This shows a bit very small. Okay, but it should be, it is not, though picture shows a small, its importance is more. And this is complex 2, this is complex 3, complex, this is cytochrome C, this is complex 4. We mentioned protons are transported vertically. In this, that means protons are being transmitted in this direction, from complex 1 to this direction, complex 3 to this direction, complex 4 to this intermembranous space. This is the intermembranous space. In here, this is the outer membrane. The outer membrane is here. So this is inner membrane, this is outer membrane. Ultimately, what happens? The concentration of the protons are increased many times in this membrane space. That means in between inner and outer mitochondrial membrane, and ultimately it tries to penetrate into the matrix. This portion is matrix, mitochondrial matrix, but it cannot. Because this inner mitochondrial membrane, it is very tough, not allowing electron to flow through it. But it can pass through this one point, this point. This is the proton. Yes, I mean these protons cannot pass. These protons can pass only through this proton transporter. This proton transporter. This is complex 5. While passing through it, it activates this complex 5. It activates ATPase. As a result of activation, it is the ADP is phosphorylated to ATP. ADP is phosphorylated. In this is matrix space, it is rich in ADP and inorganic phosphate. And inorganic phosphate is bound to ADP, forming ATP.